Hello, good morning, good afternoon, and good evening, wherever you are with respect to your time zone. Thank you for showing your interest for this topic on memory profiling of Java-based microservices architecture. My name is Gururaj Kulkarni, and I am a distinguished member of technical staff. And along with me, I have my colleague, Cherami. He is also a distinguished member of technical staff at Dell Technologies. We both representing the Dell Technologies, and we are part of data protection team in unstructured secondary storage division. Next slide. So here is the agenda for today's topic. Before we cover about Java-based microservices memory profiling and performance consideration, let's look into a very high-level overview about a microservices architecture and how it is evolving as an architecture choice, and how does it differ from the monolithic architecture, and some of the challenges we face when it comes to microservices testing. Then we will talk in detail about the Java-based microservices performance consideration, detailed memory segments, and then the performance tuning recommendations, and then the monitoring consideration for the Java-based microservices. And then finally, we have a case study to talk about how we have implemented the resource observability for the Dell Enterprise Data Protection Software, which is our PowerProtect data manager. That is built with the distributed architecture, and it has a set of microservices, how we have implemented the resource observability. And we will have a question and answers. Next slide. So microservices architecture is not a new, right? So it is the buzz in the industry now, and it's evolving as an architectural choice for many of the software product development. And microservices architecture helps to build the application with a distributed, loosely coupled, and independent deployable component. So in this architecture, the services are self-contained, and each service can be independently deployed, developed, and packaged, and then it can be tested in isolation. And these services uses the asynchronous as well as synchronous communication mechanism. And we will see in later about how does this communication mechanism can influence the performance of the service itself. This architecture uses the API for a message-driven communication between the services, and they are resilient by design and efficiently scalable by enabling the scale-up as well as scale-down architecture. So since each team can independently design, because this architecture helps to decentralize and decoupling the nature, so it helps the team to independently design, develop, and validate the services without having to have a much dependency. And this architecture methodology better fits for a Scrum at scale model, where it helps to achieve the maximum velocity. And another key advantage of the microservices is that it decomposes the business capability to a small set of independent development components, so that this architecture methodology helps to isolate the service and test it and achieve the faster innovation with faster time to market. Next slide. So now let us see how does the monolithic architecture differ from the microservices based architecture, or how does the microservices architecture performs better to the monolithic architecture, right? So in the monolithic architecture, the components have a tightly coupled communication mechanism. Monolithic architecture based application would generally combine the different components into a single large platform using a single program. So you can think of having a single JVM serving multiple capabilities, and that JVM is a kind of a one service serving the multiple capabilities with tightly coupling communication mechanism, with a data access layer having a common data access layer to the persistent DBs. So for example, in a monolithic architecture, the UI business logic would leverage a single persistent DB for the data access. But there are some companies or some teams prefer this monolithic architecture because there are pros and cons to it. The pros includes, or the advantage of monolithic architecture is, it is a good choice for a project when the modules are interdependent and interconnected. And applications built using the monolithic architecture are easy to deploy and test because number of components are very less. But the other side, which is the con, which is the disadvantage of the monolithic architecture, is the fault tolerance. Because of the tight coupling components, a simple failure could stop the whole application to function properly. And oftentimes, it's very complex to maintain as the application grows or the code base expands. So in contrast, the microservices architecture helps you to decentralize the components, and each service may have its own data access, and it uses the distributed architecture with a loosely coupled communication mechanism. As you can see that each service has its own data access, and they are leveraging those data access to talk to to achieve certain business capability. And today's most of the modern applications, such as cloud native application, e-commerce applications, are built using the microservices based architecture. And since they provide the decentralized decoupling mechanism for during the development, so one of the biggest advantage of microservices is easy to develop, test, and deploy them. And they provide the much increased agility because independent team can work on those different set of microservices without having to have any dependency. And they have a much ability to scale efficiently because you can deploy them as a single entities, right? And then they provide a faster innovation because each team can drive the development activity independently. But also there is a complexity, right? So every architecture has its own complexity. Like similarly, the microservices architecture can also create a complexity. In case if the number of services are very high, then the testability itself can be one of the challenge. So while the microservices architecture provides a better distributed and the decoupling, but the testability can be very, sometimes it can create a problem. In a single monolithic application, test boundaries can be more easily established. While with the microservices, we can have a set of hundreds of services that operate together to serve the different set of business use cases and are prone to change more rapidly. So there is a demand for more automation as you adopt this kind of a architecture methodology. And sometimes the security concern could also be one more challenge. If the service boundaries, if there is chances of attack surface could be high and can happen if there are no security measurements strictly implemented between the service communication. If any external API that got exposed has a service, the security loophole can get into the application into the security problems. Right? Next slide. So in many ways, testing a microservice application is no different than the testing an application built using other architecture. However, with more number of services, the testability of the microservices architecture could be challenging unless you consider the service isolation and test their capabilities individually. So you need to isolate these services, test the boundaries, then before you deploy it into the production, so that you can control these. Like before you get into the end-to-end testing, you can get each individual service performance boundaries as well as its capabilities, right? So the services within the microservices-based application uses the well-known technologies such as a REST or a message queue. As you can see here, these communication mechanisms can also influence the performance of the service itself for achieving the maximum throughput. And these communications can be classified as an orchestrated communication or a reactive communication. In the orchestrated communication, the API calls are typically uses the synchronous request and the response flow, and will often uses the REST-based services. In the example shown here, for example, like a portfolio service needs to have a certain, needs to update its portfolio, and it has a dependency on the account service. So the portfolio service is communicating with an account and the code service via the REST interface, and executing the like isolated test for a portfolio microservice could be a challenge because portfolio microservice is also dependent on the account and the code service, which may also needs to be deployed along with the portfolio microservices because there is an outbound communication dependency on the account and the codes. But this kind of a dependency can be reduced or can be avoided by using the service virtualization, or like you can isolating that by isolate the portfolio service and have the stubs or the mocks for the account service to replay the the APIs which are outbound from the portfolio service. Right? You can still test using the testing techniques like such as service virtualization, which are one of the advantage of the microservices based architecture. And whereas in the reactive communication, the reactive based architecture uses the loosely coupled or non-blocking with asynchronous APIs. And the set of services uses the message driven communication to communicate each other between these services. And the reactive communication is also called as, sometimes, like you can see this as like a choreography pattern or a message driven pattern. And in this pattern, microservices do not directly reference each other. Instead, they push the message into the event stream, and to which the other microservice subscribed and then act on it. These are generally non-blocking API calls, whereas in the orchestrated communication, those are blocking API calls. So in this example, let us consider the same scenario where the portfolio service needs to update its portfolio by having a confirmation from an account service. So what portfolio service does is it sends the message, it publishes the message into the event stream, and then notifies the account service, and then the account service gets the notification and it acts on that account on that particular notification, and it processes the business use case and then sends back the same message back to the event stream, and the portfolio receives that a message. And then once that portfolio receives that message, and the portfolio service can update its portfolio. Right. So here the portfolio service, when it is publishing the message, it's not really waiting. It is blocked. Unlike the orchestrated communication, it is actually unblocked. It can process its other requests as well. Right. But there are trade-offs as well. With an asynchronous, there is a trade-off of latency. With an asynchronous, the trade-off of asynchronous nature of event make it harder to understand. Right. This could be a cascading failure with an unexpected result if not handled carefully. Right. Next slide. Yeah, so now let us look into the performance testing consideration, right? The performance for the microservice based application can be measured for integrated application as well as service in isolation. Like I mentioned, you can isolate the service and test its capabilities or the boundaries. The performance evaluation for service in isolation would help to keep the performance issues much under control. If you isolate that and test it, it will be very, very helpful for you to understand its capabilities and the boundaries. So there are various performance factors that might affect when it comes to a distributed application. And let us see what all those factors that affects the microservices. So some of the factors are listed here. So the first one is the request and the latency incurred during the CRUD calls. Generally the microservice performance can be measured by having how much it is achieving the throughput, how much concurrent operations it can process with a minimal latency, right? And how fast it is actually processing those. And sometimes, like I mentioned, the type of communication can also influence the performance, which is the latency incurred, which is a synchronous communication, versus not latency incurred, which is asynchronous communication. And the third one is the processing, which is the processing of the request can also affect the performance, whether the requests are processed sequentially, one at a time, or they're getting batched in a single API, and then it is issued to the other service. The batch API performance would be ideally good for the database service kind of communication. For example, if you are doing one query at a time, right, instead you can batch those queries and single issue the one API, which can be processed in one single API with a batch of requests. And when it comes to monitoring of the resource usage, there are generally two important methods, or maybe like industry uses these kind of methods for the monitoring of the microservice and resources. And these are referred as RED and the use. So RED refers to request rate, error, and duration. Whereas use is utilization, saturation, and errors. So where are these used, right? So basically, the RED method focuses on measuring the things that end users mostly care about. For example, when using the web services, you might needs to assess how fast the web application is handling the traffic with no disruption. So in the use method, of course, more it focuses more on the monitoring of the performance, and it can actually help in identifying the root cause of the performance by measuring the utilization data, saturation, how fast the resources or the service is saturating. So it can help in identifying the root cause of the performance issues and other system related bottlenecks. So for example, identifying the memory related constraints for the Java based microservices, you will generally prefer the use kind of a model. So now with that, I will hand it over to my colleague Cherami. He will talk about memory profile of the Java based microservices and set of the memory related tuning factors when you design the microservices for your Java based microservices for your consideration. Some of the aspects of the tunings, parameters, and as well as monitoring consideration. So I'll hand it over to Cherami. Over to you, Cherami.
Okay, thank you, Guru. So during our system performance tuning and monitoring, we found that the memory is one of the biggest challenges to us. So let's review the Java memory model first. As other process, Java service also has the RSS and the swap. The RSS is the physical memory usage, and the swap is the optional. Depends on the Linux kernel whether it think the based on its system resource usage and the system parameter setting, like the swapness, it would swap out the some memory page to the disk. Those can together compose that the total memory usage of the process. And the total memory usage consumed by the heap, non-heap, and the native. And the heap and the non-heap, that can be tracked by the JVM with its native memory tracking functions. And the native part cannot be tracked by the NMT. And inside the non-heap part, there are so many other smaller types. For example, the meta space is stored class definition. The code cache store the code cache convert from bytecode to the native code to accelerate the execution performance, and also the GC part that's track the heap usage, and the symbol table that store the constant pool, and there's many other smaller non-heap types. And regarding the heap, there's in fact the whole commit the heap divided to two parts, and some of the heap is used and some of not. And this is a very important concept. We will talk later in later slides. And the heap also can be divided to young generation and the old generation, and the young generation can be further divided to EDN and the two survivor parts, like the heap metaspace also can be divided to smaller segments, like the metadata that store the class definition, and also the class space that store the class reference. And like we will mention in later slides, if we enable the application class data sharing, there are some additional parts regarding the metaspace called shared class space. If we use the Java 17, there's additional metaspace parts. And the code cache also can be divided to different segments. The first one is non method that store the JVM internal method, and also has the profiled non method that store the short life and the lightly optimized code cache. And we also have the non-profiled non-method segments that store the long life and fully optimized code cache. And regarding the native, it's also a significant memory consumer that's typically consumed by the direct byte buffer, map files, and allocated by some native libs, and also the malloc overhead. So that's the whole memory model. And as Guru mentioned, there are so many benefits of the microservice architecture, but it also has some side effects, especially the Java-based microservice architecture. With more number of the Java service, there's a high duplicate content in the metaspace, code cache, and the symbol, because they share the same JRE framework like the Spring Cloud, Spring Boot, and many other third parties. So most of them are in fact the same thing, right? So and each Java process would load those things at the same time. And in other parts, like the thread, heap, and the native, they are also have some level of duplicate because they also have the same class instance across those services. That lead to more memory, more physical memory usage, right? And as mentioned earlier, that's also increased the complexity of the operational management, including loading the same jar files, which would cause some peak resource computation. And we also need to manage each service and maintain the service status. And this service also has some dependency at start time and also at runtime. And regarding the start time, as mentioned earlier, there are some duplicate things and loading and initialization. That's definitely with the longer the start time, especially the boot time, right? And then that would have impacted the whole system resilience. So how we handle that? So we have some tuning options, especially regarding the memory and with some trade-off. The first one is the generic tuning parameters per service, like the minimal and the maximal heap size. That's most of us would know we need to control or well set these kinds of size. But there's also some other things like the minimal and the maximal heap free ratio that we mentioned earlier. By default, JVM has a 40% free ratio. That means for each Java service, at least 40% heap memory is occupied but not used. And what's the means of the max heap ratio? For example, one Java service have 1 GB committed heap size, but the really used heap size just 300 MB. And with the default JVM max heap ratio, that's 70%, which means there's a 700 MB memory committed but not used. That's a great waste, right? So if we can adjust the max heap ratio to some other value like the 40%, then we can release 500 MB memory to the system for other purpose. And another big item is the code cache size. JVM have default 245 MB code cache size, and each service would have this kind of settings. So if just many number of this code cache, then maybe we can also control the maximum code cache size to some smaller level to optimize the total memory footprint. Okay, so another choice is about GC algorithm, right? Currently, the production level GC algorithm is parallel, and the G1 CMS already deprecated since the Java 11, and there are some other experimental GC algorithm like the Shalando and CGC, but still not mutual enough. So different GC algorithms have different GC throughput and the latency, and they also have different memory footprint. So for each different Java service, we can choose different GC algorithm for better memory footprint or other factors such like the throughput and the latency based on the scenario, right? And Java also provides some advanced feature called application class data sharing that can share class definition and constant pull across the Java process, which also can be leveraged across the Java process running inside the Docker. So which can reduce the memory overhead and the startup a little bit. We also can choose different Java version. The first one is Java 8. Even is already out of the premier support, but still many products still use the Java 8 because it's mutual and also less memory footprint. But I want to mention here that Java 8 don't have the APVCDS functionality, and Java 11 does have the application class data sharing that can reduce the memory and start time. And also we have the Java 17. We have the further advanced feature called dynamic application class data sharing that can further simplify the APVCDS from the 3 steps to 2 steps. There's also some other alternative JRE, like the OpenJNI from the Eclipse Foundation. It enables the application class data sharing by default across all Java process without any additional steps. But there are some third-party components not compatible with this OpenJNI GRE, like the Elasticsearch. And also there are some different native memory allocation lib that can help us on the memory allocation. Linux default use the glibc, but there are some other alternative choice for us. That's JE-malloc and PT-malloc or TC-malloc. So we can evaluate other alternative choice based on our scenarios. So besides the memory, we also can know other metrics when we need to measure our performance. That include the CPU utilization for each service, and also the GC event and the status, especially the GC time for the full GC and the meta-space GC. If there's a high swap usage, this would become a big concern for sure. And there's also the thread usage we need to focus, right? And the total thread number, and we also can categorize different thread to different types that can help us to identify the issue point whenever there's thread issues. And we also can monitor the Java class numbers, like the loaded class number and the unloaded class number. And we also can keep eyes on the total file and socket descriptor. The Linux has the limitation regarding the total file descriptor across the whole system, right? So after monitor these things, we can know which service maybe cause issue regarding the total file descriptor issues. Regarding the network issue, we can monitor the TCP connections, include their status, right? And we also need to keep eyes on the request, especially the concurrent request running number and also the queued number. About the persistent DB, we can focus on the disk IOPS and also the response time and the typical CRUD operations. With these metrics, we can have some tool to help us to analyze the system issues. Guru would share the detail to us. Over to you, Guru.
Thank you, Cherami. Next slide. So what we have is, like Cherami mentioned, so we have built a lightweight utility to monitor the resource utilization for our application, which is PowerProtect Data Manager software, which is an enterprise solution that provides a software-defined data protection, deduplication, operational agility, and the IT governance. So some of the key features of the PowerProtect Data Manager includes a software-defined data protection with integrated deduplication, replication capability, data backup, recover, and the self-service operation, and then the multi-cloud optimization with integrated cloud tiering, and then the centralized pane of monitoring and then reporting. This application is built using the modern microservices architecture, and it has the set of around 25 microservices within it, and it's easily scalable, and we have a distributed this for ease of deployment and scaling and updating. So, and then our product supports the protection of mission critical application such as VM, Kubernetes, NAS, SQL, Oracle, HANA, and the file system. So next slide. So what we had was the typical challenge that we have a large scale test beds, right? So that resembles like a customer environment with thousands of around 3,000 assets configured, and then around 100K copies getting created. So we have a large scale these kind of test beds which are production like and runs the production like operations such as protection, replication, and data expiration that happens concurrently on these environment. So performance monitoring and identifying the bottleneck for individual service level as well as in the entire application, like entire application and the metrics that Cherami talked about was one of the critical tasks for us for our day-to-day operation, right? So then what we did is we built a lightweight centralized performance monitoring and the observability tool to address these daily monitoring challenges. So like I mentioned, there are 25 different set of microservices running inside the PowerProtect Data Manager, which is PPDM server, to serve the different set of business use cases. So the design idea for our observability tool was to build a less compute intensive with a script-based tool to capture the consolidated list of all the performance metrics to monitor the application as well as the system health. And the application metrics that Cherami talked about, we are measuring all these application metrics, including the memory, CPU, thread, GC, and TCP connection, data related database operations, all that information. And system health also we are monitoring. So it is serving the importantly for two use cases. One is to monitor the system health, and another is to monitor the application related health. Next slide, Jeremy. So here is a very high level solution overview of our lightweight utility. So we have a performance, like a lightweight master script running on the PowerProtect Data Manager, and that has the set of collector scripts. So we have written a bunch of collector scripts, and these collector scripts can be classified as to capture the system health metrics, and the second to capture the application related health metrics. So we are capturing the system health metrics using the some of the OS commands and the utilities. And for the application metrics, we are leveraging the OpenJDK and a set of commands to capture the Java processes related metrics, such as GC, heap, thread, and the class level data. And these collectors capture the metrics once in 60 seconds. And we have built a parser utility that parses this data and puts it in a structurized format for after the parsing the data, and to avoid the bloating of the space, because we don't want to have a much compute operations on the PowerProtect Data Manager except measuring the application and the system health. So what we did is we are not really storing much data here. So we have a separate dashboard server. That dashboard server actually has a cron job, and that cron job fetches the log utility. It has a log utility that fetches these log data on the daily basis and puts it in the automation server. So single dashboard server can monitor multiple, multiple PPDM servers, and we are monitoring 3 to 4 PPDM servers from a single dashboard utility. And it has the script, which is a Python-based script. And using the Streamlit and the Plotly library, we have implemented the dashboard which projects the information in the GUI format. So this dashboard has a lightweight web server provided by the Streamlit library, and there is a Python script that uses the Streamlit library to display the performance metrics on the dashboard. So currently using this tool, like Cherami mentioned, we are able to identify some of the key performance related issue, and we are actually able to tune our application. Which one of the things that Cherami talked about is how we can size the free heap ratio, and how we can size the GC related algorithms, and how we can size the heap settings. And then more importantly, the metaspace using the app CDS. We are actually measuring and tuning and applying So this is like a cyclic process, right? So we are using this tool to for our monitoring on the daily basis, and then looking into the tool to identify the key bottlenecks from the application, and we are fixing those applications. And this is our IP. So it is being used for the dev test environment as well as monitoring the customer profile test environments. Next slide. So let me. This is the kind of almost like a final slide. So performance is an art, right? So where your innovative thinking to unearth the problem requires carefully crafting the application and by monitoring the set of key attributes to identify the bottlenecks. So you need to demystify the performance factors that affect the whole system and application components, and then monitor carefully. So consider the tuning parameters like we suggested. Some of those tuning parameters you might tune depending on your application, because there is no golden rule to tune everything, right? So sometimes the tunings with too much or too less might affect the system for overutilization as well as underutilization. So you need to size the application or size based on the some of the best practices, right? So with that, we come to the end of this presentation. Next slide, Cherami. So we would like to thank you for investing your time and attending this presentation, and hope you found it interesting and your feedback is really valuable. We don't want to stop here, but you can still reach out to us using the mail IDs mentioned here, and your feedback is very valuable to us. Please share your feedback, and thanks for attending this topic. Thank you very much.